This is the third part of our study of integer division, the division algorithm. And here's the idea. Even if a does not divide b, a and b are integers, you can still divide b by a and get a quotient and a remainder. And that is essentially the content of the division algorithm. So before we look at the formal statement, let's try an example. So we want to divide 68 by 7. The division algorithm says that you can divide 68 by 7 and get a quotient, which is 9, and the remainder when you divide 68 by 7 is 5. And we will usually express this in equation form. 68 is 9 sevens plus 5. 68 is 9 times 7 plus 5. Some notation that we're going to introduce. Hopefully it will make some things easier. The quotient, when you divide 68 by 7, is denoted 68 div 7. That's 9 in this problem. And the remainder, when you divide 68 by 7, that's the 5 in this problem, is denoted 68 mod 7. The div notation is not very standard, but the mod notation is standard notation. So 68 mod 7 means the remainder when you divide 68 by 7. And here is the statement of the division algorithm, which is really a statement of a fact. It's a theorem. For all integers a and all positive integers d, you can divide a by d and get a quotient q0 and a remainder r0. And the results of the division are expressed like this. A is q0 times d plus r0. And the remainder has to be non-negative and smaller than the thing you're dividing by. So this is the equation that says you've divided a by d and gotten a quotient of q0 and a remainder of r0. And in general, we will use a div d for the quotient when you divide a by d, and we will use a mod d for the remainder when you divide a by d. So the q0 from the statement of the theorem is a div d, and the r0 is a mod d, the remainder. There's the theorem stated once more. Okay, and as I said earlier, this simply says that you can divide a by d for any integer a and any positive integer d and get a quotient and a remainder. The remainder being non-negative and smaller than d. Let's try one more example. So if a is 38 and d is 11, and you divide 38 by 11, let's see, 11 goes into 38 3 times. So the quotient, q0, is 3, and the remainder is 5. And we will usually be writing the results of the division in this form, as I said earlier. So 38 is 3 11s plus 5. 3 times 11 plus 5. And using the div and mod notation, the 3 is 38 div 11, and the 5, the remainder, when you divide 38 by 11, is 38 mod 11. let's look at two more examples which illustrate situations that might occur. Let's suppose A equals 35 and D is 7. Well, 7 is a divisor of 35, so in this case the division algorithm still applies, but the remainder is 0. Right? And dividing 35 by 7 gives you a quotient of 5 and a remainder of 0. And so Q0 is 5 and R0 is 0. Here's a second kind of thing that might happen. Here A is 17, and we're dividing by 37. We're dividing by something larger. So if you divide 17 by 37, you can't get any 37s out of 17. The quotient is 0, and the remainder is 17. So the remainder is in the right range, right? It's non-negative, and it's less than or equal to 37, the thing we were dividing by. So Q0 is 0, and R0 is 17 in this case. There's a statement of the theorem again, just as a reminder of what it says. And on this slide, we're going to look at a very brief outline of how the proof will go. So we will first prove the theorem in the case where A, the thing we're dividing into, is non-negative. And the plan for the proof is, given a non-negative A and a positive D is always positive, we let capital A be the set of integers Q that are between 0 and A over D. And then the proof will consist of arguing that A is non-empty and bounded above. See, those two parts are fairly clear. Q equals 0 is in A. It's an integer and it fulfills this inequality. And A over D is an upper bound. The upper bound is sort of built into the definition. So A is non-empty and bounded above. We will use the greatest element property to get a greatest element of A, and that'll be the Q0 that works. And then to find R0, we look at this equation that's part of the theorem. If we want this equation to be true, there's really only one choice for R0. R0 has to be A minus Q0 times D. So a few details left out, but that's an outline of the proof, and we'll look at it more fully in the exercises. So here's an example that sort of illustrates how the proof of the theorem would go in a specific case. So if A is 38 and D is 11, we've already looked at this example. We got a quotient of 3 and a remainder of 5 when we divided. So with this choice of little a and little d, the set capital A would be the set of integers which are greater than or equal to 0 and less than or equal to 38/11. So 38/11 is between 3 and 4. That means that the set capital A consists of the integers 0, 1, 2, and 3. Right? 4 is not in capital A because 4 is not less than or equal to 38/11. And the greatest element of this set is 3, and that would be our Q0. And as we know, 3 is the quotient. And then we would construct R0 from Q0. R0 is going to be A minus Q0 times D. A is 38. Q0 is 3. D is 11. And doing that calculation gives us the remainder, which is 5. So Those two slides illustrate how the proof of the division algorithm will go. If all you want to do is find the quotient and remainder, you don't have to do a proof. Right? Things are easier, even with relatively large numbers. We are still assuming that a is non-negative here. So let's look at an example with fairly large numbers. Let's suppose that a is 52,835 and d is 305. So I divided a by d on my calculator, and I got 173.229508. So that means the quotient, when you divide 52,835 by 305, is 173. So Q0, the quotient, or using the div notation, 52,835 div 305, is 173. And now we need to calculate the remainder, which we do using the formula. The remainder has to be a minus Q0 times d. So the a in our example is 52,835. In step 2, we found that Q0 was 173 and d is 305. So doing this calculation gives us the remainder, which is 70. So writing the result of this calculation in equation form, 52,835 is the quotient 173 times 305 plus the remainder. Now we are going to look at the case where a is negative. So we know how to calculate the quotient and remainder when a is non-negative. What do we do when a is less than 0? And I'm going to illustrate the procedure by looking at this example. A is minus 52,835 and d equals 305. Almost like the previous example. Okay, so we know how to find the quotient and remainder for the absolute value of a. Right? The absolute value of a will be a positive number. In this case, 52,835. So we calculate the quotient and remainder for the absolute value of a. This was our last example. 52,835 is 173 times 305 plus 70. Now, we're going to multiply both sides of this equation by minus 1. The idea is that we are interested in dividing minus 52,835 by 305. And if we multiply both sides by minus 1, we will have the value of a that we want on the left-hand side. The problem now is that minus 70 cannot be the remainder. Remember, the remainder, when you use the division algorithm to divide, has to be non-negative. So we need to make a slight adjustment to the right-hand side of this equation. And the adjustment we're going to make is we are going to add 305 to the minus 70, and we are going to subtract 305 from the other term. So we're adding 305 to minus 70, we're subtracting 305 from the first term of the right-hand side. If you do that, you get this equation. So still minus 52,835 on the left. On the right-hand side, we have minus 173 times 305, and we have subtracted 305. And then the minus 70, and we have added 305. If you do a little bit of calculating here, calculating in algebra, you get minus 52,835 Now if you combine these two terms, minus 173 times 305 minus another 305 will give us minus 174 times 305. And minus 70 plus 305 is 235. 235 is in the right range to be a remainder. It's non-negative and it's smaller than 305. So here are what the results of the division algorithm look like in this example where a is negative. The Q0 is minus 174, and the R0, the remainder, is 235. So here in general is how you find the quotient and remainder when a is negative. Basically, I'm just going to follow the example on the previous slide. Okay, so we have a negative a. We know how to find the quotient and remainder for positive numbers, so instead of looking at a, we start with the absolute value of a, which will be positive. We find a div d, and we find a mod d. The quotient and remainder when you divide the absolute value of a by d. Sorry, we're finding absolute a div d and absolute a mod d. And we're calling them Q1 and R1. So this we know how to do. You can write the absolute value of a as a quotient times d plus a remainder, where the remainder is in the right range, less than or greater than or equal to 0 and less than d. And now we're going to multiply both sides by minus 1. In just a second, actually. There are two possibilities. The first possibility is the easiest of the two. If the remainder, when you divide the absolute value of a by d, is 0, then the absolute value of a is q1 times d plus 0. So a, which will be minus the absolute value of a, will be minus q1 times d plus 0. So the quotient when you divide a by d is minus q1, and the remainder is 0. If R1 is greater than 0, here is where we begin by multiplying both sides of this displayed equation by minus 1. Okay, if R1 is greater than 0, then a, which is negative, will be minus the absolute value of a, will be minus q1 times d minus R1. And now we make the same adjustments that we made in the example. We are going to add d to the remainder, and we are going to subtract d from the first term of the right-hand side of this equation. The results look like this. We've added d to the remainder, and we have subtracted d from the minus q1 times d. And then doing a little bit of algebra, minus q1 times d minus another d will be minus the quantity q1 plus 1 times d. And d minus r1 I haven't changed here. And d minus r1 will be in the correct range. R1 is smaller than d and greater than 0. So d minus r1 will be between 0 and d. So the q0 that works for a, the original negative number, is minus q1 plus 1, and the r0 that works is d minus r1. So maybe a summary of all that would be a good idea. So for negative a's, you want to find Q0, which is A div D, and R0, which is A mod D, and they can be calculated like this. Q0 is minus the quantity Q1 plus 1, and R0 is D minus R1, where Q1 and R1 are the quotient and remainder when you divide the absolute value of A by D. Unless R1 equals 0. In this case, Q0 will be minus Q1 and R0 will be 0. So there's a summary of the method for finding the quotient and remainder when you're dividing a negative number by a positive divisor. So let's try this on an example. We want to divide minus 7,612 by 231. We first divide 7,612 by 231. Using a calculator, as I described before, we get a quotient of 32 and a remainder of 220. So the Q1, the quotient, when you divide the absolute value of minus 7612 by 231, the Q1 is 32, and the R1, the remainder when you do the same division, is 220. And now we're going to use the formulas for calculating Q0 and R0, the quotient when you divide the negative number by 231, and the remainder when you divide the negative number by 231. So Q0 is minus the quantity Q1 plus 1. Q1 is 32. So Q0 is minus 33. And R0 is D minus R1. That's 231 minus 220 is 11. So, writing the results of the division algorithm in equation form, minus 7612 is Q0 times 231 plus R0. Q0 is minus 33, and R0 is 11. One final slide. There is a uniqueness component to the division algorithm theorem. And here's what it tells us. If you start out with two integers, a and d positive, and you find a way of writing a as w times d plus z, where w and z are integers, and z is non-negative and less than d, no matter how you find this equation, w has to be a div d, and z has to be a mod d. Right, w must be the quotient when you divide a by d, and the z must be the remainder. We'll look at completeness in the exercises.